this topic, we're going to look at the origin of the colour of a transition metal. How does it actually arise? And secondly, we're going to look at the factors that determine the colour of a complex ion. And it's really important that you know the factors that give rise to the colour, that you can draw diagrams of the electron transitions as well. You'll probably recognise this picture here from our aqueous ions video, and you can see that chromium ion, copper ion 2 and ion 3 and cobalt 2 all exhibit colour, apart from aluminium, and we know that aluminium has no d electrons. So we can start from the basis that transition metal ions, true transition metal ions, have incomplete d subshells. So substances appear coloured when visible light energy is absorbed by an atom, an ion or a molecule. So transition metal ions with incomplete 3D subshells form coloured ions and complexes as well. And if we look at the electron configuration of copper, we can see that copper has an incomplete 3D subshell. So copper ions have only 9 electrons in their 3D level, and the horizontal line represents their energy levels before a ligand binds. When ligands bind to the copper 2+ ion, the 3D sublevel is split to form 2 slightly different energy levels. 3 of the d orbitals, as you can see here, are at a lower energy level, and 2 of the orbitals are at a higher energy. So here you can see there are fewer electrons in the higher energy level, as the electrons are obeying Hund's rule in that they'll occupy the lowest energy level first before pairing up. So all the paired electrons are in this lower energy level here. It just so happens that an electron in the lower 3D level can absorb energy from visible and ultraviolet light and causes it to be promoted to the higher 3D sublevel. The difference in energy that we call delta E is proportional to the frequency of light absorbed, and that determines the colour of the complex. And this statement is really, really important. The difference in energy is proportional to the light absorbed, and that determines the colour of the complex. This difference in energy is equal to something called Planck's constant multiplied by the frequency of the absorbed radiation. Thus, our hexaaqua copper appears blue. So if we look at white light, we know it's a continuous spectrum with all the frequencies of the visible spectrum. Remember that the frequency of the light increases from the red end of the spectrum to the blue end, and this is the highest frequency radiation that we can see. Now, it's more common when we're discussing visible light to talk about the wavelength, and therefore if we look at this graph, if this continuous spectrum here, the frequency increases towards the violet, but the wavelength actually increases towards the red. So red light has longer wavelengths than violet light. We now look at the colours of the spectrum on a colour wheel when we're looking at the absorption of light, and we look at 2 opposing colours. This is approximately the colour of copper, our hexaaqua copper ion here, and you can see that the opposing colour on this colour wheel is red. So our copper solution is absorbing the red and yellow parts of the spectrum here because these are the complementary colours. The light that comes out on the other side of the tube is the complementary colour to the absorbed colour, and therefore a blue solution that absorbs red light appears blue-green. So here's a spectrum for a particular ion. And you could be asked, what colour does this ion appear? And you can see it's absorbing mainly in the blue, green, yellow part of the spectrum. So the blue, green, yellow. And therefore it will appear its complementary colour. And therefore this hexaaquatitanium 3 ion will appear violet. It's reflecting light in the violet and absorbing, as you can see, in the green-yellow. So it's important to note that the complex we just looked at was a simple example because it only contains one d electron, but it gets a little bit more complicated when there are several d electrons and lots of different transitions are possible. But the basic principles are the same. There are 3 factors that affect the colour of a transition metal, and that is the number of d electrons, the arrangement and the type of ligand surrounding the central metal ion. So it's the arrangement of ligands and the type of ligand. Let's have a look at this ligand exchange reaction with copper ions. So the light blue colour solution is caused by this hexaaqua colour here. And you can see as the complex forms, just ignore the precipitate for now, as excess ammonia is added, it goes deep blue. And the absorption spectrum changes. So this is the absorption spectrum of the light blue solution, and this is the absorption spectrum of the blue-violet. You can see that the blue-violet, or this complex here, the tetraamino diaqua complex, which is blue-violet, is absorbing at a shorter wavelength, so therefore a higher energy gap. In the deep blue complex, light of a higher energy and therefore smaller wavelength is being absorbed. So change in ligand can affect the absorption of light in our complex. Here are 3 different complexes. They're all hexaaquat ions, so we have copper, iron and cobalt. Copper 2 is blue, iron 2 is very pale green, and cobalt 3 is pink. So clearly the energy gap is different for each of those transition metal ions. And remember, at the start, we said this is affected by the transition metal ion itself, the nature of the ligand, well, these have all got water molecules, and also the oxidation state of the transition metal as well. Let's now have a look at some of the calculations involving delta E. Make sure that when you come to answer an exam question on this, in the origin of colour, you draw a diagram showing it's the ligands that are splitting the D subshell, and that it's the energy absorbed when an electron gets excited to a vacant D orbital, and it's the size of this energy gap. And the size of the energy gap depends on the number of d electrons, the arrangement of ligands, because that causes the splitting, and the nature of the ligand. An important transition metal to possibly remember is vanadium, because vanadium gives rise to 4 different colours in 4 oxidation states, going from the lowest, that's vanadium, which is violet, vanadium 2, to dioxovanadium 5, which is the yellow species. They're all in aqueous solution, so the oxidation state also affects this energy gap here. So what colour light do you think the vanadium 5 solution is absorbing? This solution here. Look at the colour wheel, and you know that it's absorbing in the violet part of the spectrum. It's absorbing a higher frequency of light. We then go to the lower oxidation, the +4 oxidation state, that is absorbing in the red part of the spectrum. If we go to the green, you can see it's absorbing in the indigo red, and the final solution there of vanadium 2 is obviously absorbing in the green part of the spectrum. So it's important when you're manipulating that equation that you know that the energy of the radiation is equal to the Planck's constant times the frequency, and you'll always be given Planck's constant. And also remember that frequency is the speed of light divided by the wavelength of light. So just make sure that you can manipulate these equations. As I said, you will always be given these constants. So the first question here is, a photon has the frequency of 2.68 times 10 to the 6 Hertz. How would you calculate its energy? Well, obviously you're going to substitute that straight into the equation. E equals h times the frequency, and that's dead easy because you simply then substitute in the value for Planck's constant, 63, times 10 to the minus 34, times the frequency of the radiation in Hertz, which is 2.68 times 10 to the power 6. And that will give you our answer in joules. In the next calculation, you're asked to work out the wavelength of light given the frequency. So first of all, we can work out the energy. So that's h times the frequency of irradiation. And then we need to rearrange that to get the wavelength on its own. So that's this equation here. So simply we've swapped places with lambda, which is wavelength, divided it by E. And the answer there comes out to 4.87 times 10 to the minus 7 meters. In the next question, you'll be given the length in nanometers, and you're asked to find the frequency and the energy of blue light that has this particular wavelength. So what you now need to do is rearrange this equation here to get the energy and the frequency. So the first thing to do is to rearrange this equation here for frequency, but don't forget to convert your nanometers into meters. So once you've got your frequency, which is 7.5 times 10 to the 14, you can then use this equation here. So you've got the frequency times Planck's constant to get the energy, which is 4.97 times 10 to the 19 joules. Pause the video and see if you can answer questions 4, 5, 6 and 7. Pause the video now. So question 4, did you get that energy equals 9.95 times 10 to the minus 19 joules? And for question 5, did you get the energy equal to 3.98 times 10 to the minus 22 joules? The answer to question 6 was 5 times 10 to the power 22 photons. And question 7 was 1.01 joules. In this section, we're going to look at the idea of colorimetry. So before we do that, yesterday I was in the lab and I took some 2 ions and some potassium thiocyanate. And potassium thiocyanate contains the thiocyanate ion, SCN-. Let's see what happens when you mix them together. Here I'm about to take some of the iron 2 sulfate and put it on my palm, and then I'm going to put some of the thiocyanate ions on the palm, and lo and behold, I start to bleed. So that is theta blood, and it's a complex form between the iron and the thiocyanate. How do we find the formula for theta blood? In doing research, I found out that it's actually iron 3 that gives the blood red solution. So there must have been some oxidation over the long lockdown that caused some of the iron 2 ions to be oxidised to iron 3. So it's the iron 3 that has formed a complex with the thiocyanate. Of measuring the intensity of that colour that is produced when the iron 3 and the thiocyanate ions are mixed together in known quantities. So to find the formula of that complex, we need to measure the intensity of that colour of the solution, or how it's absorbing visible light. This is a more dilute solution, and you can see as it gets more dilute, more light is able to pass through it. The instrument you can see below is a simple colorimeter, and the colorimeter has a display on the front here, and what we can do is we can change the colour of a light that is passing through a solution that goes into this well here. So if I just zoom into that well, we can see at the moment a blue LED is flashing, and that means that blue light is passing through the solution at that point. We now change the LED on the display down here. We can now pass red light through our solution that's placed in that little well, or we can pass green light through it. So we've just made a red solution, and therefore that means the light. I pause the video at this point because which colour of LED do you think would be complementary to our red solution that will give the greatest absorbance? Whilst you're thinking about the colour of LED that we use, we first of all need to make up a range of solutions with varying ratios of the Fe3 and the thiocyanate. So we can do this in test tubes using graduated pipettes to measure out exact volume so we know the exact ratios. What we now need to do is take a sample from each of the test tube and put them into the special containers that will go into that well, into the colorimeter, and these are called cuvettes. So we transfer a sample of each into the cuvettes and then into the colorimeter. Remember that we need to calibrate the colorimeter with a colourless solution of water. So water will always be used to calibrate the colorimeter, and we'll set that to absolutely zero absorbance. So the water is used to calibrate the colorimeter, and we can use it to set to zero absorbance. Here's a graphic of the colorimeter. So in our case we have an LED source as well as the light. So that was a light emitting diode, and in our case it gave green light which then passes through the solution. So in our colorimeter we didn't need a filter. So the green light passes through the red solution. Any light that is able to get through then goes to a light detector. So clearly the darker the sample, more concentrated, less light gets through to the detector. So the absorbance increases, the absorbance of the sample increases. That then goes to a data logger, or in my case it was recorded on my mobile phone. As we put each tube in the colorimeter and a reading of the absorbance was taken, we put this into a table. So you may be asked to design a suitable table. So then from our data, a graph of absorbance that we got from the colorimeter is plotted against the solution mixture. And what we then do is plot a graph. So let's now have a look at the graph. From the graph, it can be seen that the maximum absorbance occurs in tube 5. And then after that, adding more thiocyanate ions made absolutely no difference. And therefore, that showed that the ratio of thiocyanate ions to Fe3 plus ions in the complex. So let's go back to our table. From the table, it's clear that in tube 5, we've got equal amounts, that's moles, we've got the same volume and concentration of Fe3 plus ions to thiocyanate ions. So their ratio in the complex must be 1 to 1. Let's write an equation for that ligand substitution reaction. So we have the hexa-aqua Fe3 plus ion and the aqueous thiocyanate ion, and they react together in a ratio of 1 to 1. And this means that the formula of the complex, all of the water molecules must be substituted and be replaced by one thiocyanate ion with a negative charge. The charge on the new complex must therefore be 2 plus, and that is your blood red colour, and 6 waters are substituted. This is an example of a summary question from your Kubeidl textbook. Let's see if you can answer it. So the question asks you, it shows you the absorbance of a series of mixtures containing different proportions of the same concentration, one containing nickel 2 ions and the other containing the EDTA ligand. The two solutions react together to form a coloured complex. So it says which mixture absorbs most light, which mixture contains the highest concentration of the nickel EDTA complex, and therefore what's the simplest empirical formula of the complex. Pause the video, work out your answer, release the video and see if you got it right. Looking at the graph, the greatest absorbance are where the nickel and the EDTA are in equal proportions, and that means nickel reacts with the EDTA on a 1-to-1 ratio. So let's now write an equation. The hexaaqua nickel is substituted by the EDTA ligand, and remember from before that this is a hexadentate ligand, and therefore the resulting complex is 1 nickel to 1 EDTA. U charge is 2 minus, 2 plus and 4 minus is 2 minus, and we have 6 water molecules substituted. The nickel EDTA complex is going to be very, very stable because of the chelate effect. On the left hand side we have 2 species, on the right hand side we have 7 species. To summarise, therefore, in an exam, if you're asked to describe how to measure the formula of a complex, remember you would use a colorimeter, state why, because of the fact it absorbs colour. You choose a suitable filter or LED which gives the maximum absorption for the complex. You make up your range of solutions, you measure each of their absorbances and plot a graph. And then you would plot a calibration curve or concentration versus absorbance. You then measure the absorbance of the solution of unknown concentration and use the calibration curve to find its concentration. We can also use the colorimeter to find the rate of a chemical reaction, because in a chemical reaction where there is a change of colour, for example in the reaction with manganate and sodium ether dioate or oxalate, we can measure the decrease in concentration by decrease in colour over a period of time. Let's take a quick look at that experiment. Thinking back to our transition metals behaving as catalysts, we know that the reaction between purple MnO4- ions and ethane or colourless ethane dioate ions is autocatalytic because the two negatively charged anions are really not attracted to each other. As the reaction proceeds, some of the Mn2+ ions produced then autocatalyze it. Let's see how we can use our colorimeter to measure the rate of this reaction. Back again, and what we can see here is the curve is starting to be produced. Let's look at the table of data that is being collected. So we can see that every second data is being collected, and you can see here that the absorbance is definitely decreasing over time. So we go back to the graph on our, there we go, there's the graph of the results. As time proceeds, you can see the absorbance is dropping. Now what's the most important thing is going to be the shape of this graph. So again, we're going to come back in another couple of minutes. The colorimeter is therefore a perfect data logger for looking at the autocatalytic reaction. So we can see the concentration, which is directly related to the absorbance, first of all decreases really slowly until the Mn2+ ions are produced, and then reaction speeds up. And as the reaction stops and the reactants are used up, it then levels off. And notice here we used a green filter with our purple solution, and we used absorbance. As the solution got less intense in colour, the absorbance of light decreases. You should be able to replicate this graph, this sketch graph in an exam, and also you should, from the transition metals, be able to work out this balanced redox equation. So remember, the catalyst, the Mn2+ ions, are not present at the start, but once a little manganate is produced, it then reacts with the MnO4- ions to produce Mn3+. And this is an intermediate species, so if we move this up and have a look, remember the intermediate Mn3+ species then reacts with the ethane dioate to produce carbon dioxide, and then the final product, Mn2+ ions. So like all catalytic reactions, one species, in this case the manganate, gets reduced to Mn2 plus, and some of the Mn2 plus ions then get oxidized to Mn3 plus ions. The Mn3 plus in turn get reduced back to Mn2 plus ions, and the reducing agent is the colourless ethane dioate, the C2O42 minus ions, which in turn get oxidized to carbon dioxide. So there's a reduction and a simultaneous oxidation, and then a reduction and an oxidation. The transition metal, in this case the autocatalyst, is the Mn2 plus ion, which gets regenerated at the end. It's likely that the Mn3 plus ions get complexed by the bidentate ethane dioate ions, I'm just drawing the skeletal formula here, that donate a pair of electrons to the central metal ion. And the bonds on the ethane dioate ions get weakened by the highly polarizing Mn2 plus ion. So this complex Mn3 plus ion, so this is a 3 plus complex, and the overall charge is 3 minus, and these bonds here get weakened by the very polarizing Mn3 plus ion at the top. In weakening these bonds, it therefore lowers the activation enthalpy for the reaction.